it's better.
Okay. Yeah. Thank you for the introduction, and sorry for the delay to solve some technical challenges. Yeah, it's my pleasure to, and for both of, or it's our pleasure to give the best practices from the field talk, and to talk how to enhance the epitaxy process performance by in-situ data. And yeah, my name is Oliver Schulz, and together with me is Heiko.
Yeah, hello everybody, also from my side. Thanks to all of you for participating, and special thanks to LayTec for inviting me as a co-speaker in this seminar. Yeah, my name is Heiko Mettler, and typically Oliver and me, we are working pretty close in our daily service and support business.
Yeah, the outline of our talk. So we will start with some general remarks concerning the talk, and then Heiko will present and explain why state-of-the-art MOCVD production requires advanced in-situ metrology. I will explain how LayTec's in-situ metrology will get you there. We will talk about the major part of the talk will concerning the most important parameter for MOCVD growth, the true temperature, and correlated with that typical issues what we received from the field. To improve your work, we will give some recommendations for daily operations. And finally, we will make some conclusions, and we will give you an outlook for the next future. The general remarks. Aixtron and LayTec are honored to give the first time ever in tandem talk in a seminar. We will hope to get it much more often. This talk will focus on general approaches, how in-situ tools are used to improve the MOCVD-based production process. Due to IP reasons, we cannot cover very specific topics, Aixtron LayTec interactions, for example, reactor to reactor, system to system matching, or we cannot focus on very specific growth improvements. So, but for LayTec Aixtron customers, we offer in direct contact for specific seminars or just information exchange. So you can feel free to contact us via support@LayTec or Tech Support Germany, or contact us directly, me and Heiko as well.
Yeah, I will also be happy to answer all your questions if you address them directly to me, to my email address, or even to our Aixtron support group at Tech Support Germany at aixtron.com, and we'll be happy to answer your questions as much as we can. So we'll start with the question why the state-of-the-art MOCVD production requires an in-situ metrology. The in-situ metrology implies that it's necessary to directly read key figures, key properties like temperatures and reflections and other growth dynamic process parameters right in the scene of crystal growth. The key target that needs to be reached at the end of the day is an optimized cost of ownership in the entire MOCVD production chain. So that comes to the question, what needs to be fulfilled in order to reach this key property of the MOCVD production, an optimized productivity, or either way you look at it, optimized cost of ownership. So subsequently to this property, the effect will be the more in-situ metrology functions can be done in real-time process analysis and quality analysis, it minimizes the in-situ characterization efforts. Also, then the closer the process can be controlled, or can the higher the yield and the process quality properties can be brought to, it minimizes the binning efforts after the process for devices binning. Based on minimized binning efforts, the further subsequent back-end efforts further down the road towards device productization can also be minimized. As a final result, this property, or this function, will allow you to minimize the entire production cost per device, typically normalized to a production per year, or production per production cost per year, I'm sorry, or cost per a device production lot. So the overall general effect is you will achieve a maximized tool productivity, and that will directly lead to a minimized cost of ownership balance of the entire MOCVD production. So how to get there? From the very basic property of the epitaxy crystal quality on the wafer, all the way to a optimized cost of ownership of the entire production MOCVD production landscape, can be shown in a kind of developing process. So basically, you definitely need to achieve a very good on-wafer uniformity. This is an example plot that shows a pretty nice uniformity already, and the in-situ metrology functions of the EpiNet or EpiCurve TT system allows you to already monitor and adjust your process accordingly to achieve a very good uniformity in PL uniformity and in crystal morphology, growth rate, and growth uniformity. So the next level of evaluation then will definitely be a sorry, it doesn't move. A wafer-to-wafer transfer or transition. You don't only want to achieve a good, perfect epitaxy result on one single wafer out of a full load, but you definitely want to achieve the same on all wafers. So the wafer-to-wafer spread must be and will be able to be maintained within a very tight, narrow tolerance band. So then the next level of evaluation here in this process will definitely be a run-to-run reproducibility and a very tight run-to-run quality result. So what you achieve based on a very single wafer quality transfer to a full load wafer-to-wafer must then be reproducible in a run-to-run scenario that within a certain allowed tolerance band over time due to or within a maintenance cycle, it allows a very close run-to-run repeatability. Then the final level then will be once you reach a run-to-run repeatability, to transfer this to a system-to-system performance. So that means that based on run-to-run repeatability quality, the next level then will be a system-to-system optimization, which then will lead to an entire optimization of the cost of ownership at a maximum productivity of the entire MOCVD production environment. And that's basically the key target we are chasing in cooperation between LayTec and Aixtron with the implementation of the improved interaction of the LayTec epicurve TT system with the EpiNet software and the MOCVD process control.
Yes.
So Oliver will continue now with some guidelines or some information how the LayTec's in-situ metrology will help you get there.
Yeah, how we will help to get you there. And in this talk, we will focus on 3 products. The first one is the EpiTT, second the epicurve, and finally the P400 or Pyro 400. And the EpiTT is an IR, or includes an IR pyrometry, and is based on a focused LED light source in addition for the reflectance measurement, so to do the ECP correction, what we would like to explain a little bit later in the talk, and also a growth rate analysis. So the most important parameter is the temperature, so it enables you to read the true temperature on the wafer. By using the reflectance measurement, it's enabling you to do the growth analysis. And with both together, it's furthermore enabling you to control the growth process by true temperature on the substrate surfaces.
Maybe I can quickly contribute here. Control in this context does not mean a direct closed loop control, but more a more sophisticated feeding back growth analysis parameters back into the recipe design or epitaxy process design in order to implement a continuous process control improvement.
Yeah, the epicurve contains the same functionality as the EpiTT, and in addition, it has a focused semiconductor laser for the curvature detection. So that means you can do you have the complete EpiTT functionality, and in addition, it's enabling you to get the curvature detection. So curvature detection means you can monitor wafer relaxation, for example, and even more, you can do the strain engineering, especially gallium nitride on silicon requires a sophisticated strain engineering that after you have done your growth, you have, after cooling down, a flat wafer, for example. Not all layers are suitable for using an IR pyrometer. Therefore, LayTec has also in the portfolio an UV pyrometer. This is the P400 or Pyro 400. This sensor enables you to measure the surface temperature on IR transparent layers, for example, gallium nitride. Yeah, at UV wavelengths, gallium nitride at gross temperature is opaque. So that therefore in that range you are able to measure again the real true surface temperature. So, and not only to measure it somehow, it makes the measurement free from Fabry-Perot oscillations. So this is especially necessary on sapphire substrates or PSS, where gallium nitride especially is grown for LED or laser application.
Yep.
So,
yeah, this slide shows the basic general sort of low-level technology integration map, how the EpiNet or the epicurve TT system running on the EpiNet system, a software system, is implemented in a typical Aixtron MOCVD process setup. So the core unit in terms of epicurve TT function is the LayTec controller. That's the center unit you see in the diagram to the right. It's a 19-inch controller that mainly holds the main hardware that is providing the functions and the technology functions needed for the epicurve TT system. The main control instance to control the MOSVD process itself is the epitaxy control computer to the right and in the bottom area. Exact is our Aixtron process control software suite that provides direct MOSVD process control as well as advanced configuration functions and process analysis functions. And the other main instance for software control is the EpiNet computer. That's the so-called MPC unit in the top of the diagram. That computer holds and runs the EpiNet in-situ metrology software from LayTec. EpiNet has been available out in the field and running out in the field on many systems in version 1.10, running on XP, still running on many systems out in the field, and nowadays replaced by the successor of the EpiNet version 2 family. Aside from additional functions and more comfortable enhanced control functionalities and design functionality and configuration functionalities, the EpiNet software version 2 offers. The main general functionality is still unchanged within the entire control network as shown on the diagram. So the LayTec controller as the core unit is, the roof window is kicking in here. So the main core unit here is shown here is the electronic control unit. That's a 19-inch controller. It provides a bunch of network protocols for the necessary I/O for both electrical controls signals like rotation, trigger synchronization, an optional analog I/O interface, as well as digital serial protocol-based communication. The main I/O unit, so to say, for the APT function itself, the optical fiber cables. We will address some topics about the optical fiber cables in later slides as well. So those two cables run to from the light source within this controller to the inlet connector of the optical fiber head of the APTT optical head on top of the reactor, and feed the reflectance light and the temperature parametry signal back to the detector card through the other light glass fiber cable. So if you consider the LayTec controller unit and its entire I/O landscape as one functional instance, it's easy to see that the entire setup builds an entire circle consisting of a continuous data interchange loop between process regime, EpiNet control, and exact process control. Another feature which is getting more and more common, or is the application market is more and more demanding for, is the SECS-GEM interface. That's an available extension of the EpiNet I/O interfaces and allows for fab house communication through SECS-GEM. Okay, so now Oliver will now continue with some general important background information about the LayTec systems.
What is you always should keep in mind is the important background of the LayTec systems. So all systems, or all of our systems, are set for a specific optical path. That means especially the working distance and the viewport on your growth system, because this is defining the optical, or this is influencing strongly the optical measurements. In addition to working distance and viewport, the P400, because of using this UV range for the parametry, this needs in addition a stray light protected mount. So what is important to, we mentioned that the most important parameter is the temperature, so to measure the temperature value very accurate. The temperature measurement in case of parameter means how much light on the LayTec parameter equals which true wafer temperature. LayTec systems are set with a two-step approach. So we start in the factory when the system is assembled with a black body calibration, which is traceable to the Physikalisch-Technische Bundesanstalt, so the German National Standard Organization, that this black body temperature equals or is according to a real standard and showing the absolute value. And we are using for the calibration the original viewport. Yeah, so we have a set of viewports for known reactors. That we use for the calibration, finally, the same optical path what we will find on the reactor after the installation. This brings me to the second step. In the factory, we assure the linearity of the detector, so that we have a correlation between the light intensity on the detector and the temperature. And yeah, there are many reasons why we need an on-site calibration as well. The viewports might be slightly different, especially if we have smaller holes in the viewport. We need an on-site calibration. In the old days, sometimes still used is the eutectic calibration, but what we, since many years now, we recommend to use LayTec's calibration tool. This is the absolute, available for both kinds of pyrometers, the IR pyrometer family, EpiCurve, EpiTT. There it is the absolute 950, or on the other hand, the UV pyrometer, the P400. This requires an absolute 400 because you need to calibrate it for the correct wavelength. Both systems are also PTB traceable. This calibration device assures the accurate value of the temperature by making the gross temperature, and you use it below the ceiling. Well, after you have properly aligned your system, or LayTec has properly, or Aixtron has it properly aligned to the reactor setup, the next challenge is that the emissivity of is material dependent. So that means you are growing different layers, and it will change during the growth process. So the EpiT2 solution, and this is valid for the EpiCurve as well, is a continuous emissivity correction to get the true temperature. To get there, you need at the same time, at the same wavelengths in reflectance measurement, and the reflectance has to be calibrated as well. This is is very fundamental to get the correct temperature value, which means, on the other hand, if you do it in the wrong way, or it's done not properly, you will have a faulty emissivity correction, since the emissivity is 1 minus R, so 1 minus reflectance, so it has a direct impact on the emissivity correction. If R is wrong, means directly the emissivity will be wrong. If the emissivity is wrong, the temperature will be wrong. So finally, the reflectance measurement is the backbone to get the true, or what we call true temperature, the absolute temperature value on the wafer. This example is showing what will happen. The straight line in the center is the green line is if you have done the reflectance calibration properly. This is compensating the Fabry-Pore oscillation caused by the layer which is grown in the MOCVD. So you will have finally a straight line where you can read the real temperature on the wafer surface. If we would not do that, you can also display the raw voltage. That means no ECP. You will find an oscillating temperature measurement. This is the blue line below the green line. Or if you would have a wrong value for the reflectance, you might have oscillations on top of the real value. That is the black line, where we have, in this example, an overcompensation. So this is showing an incorrectly calibrated reflectance will cause residual oscillations. So we recommend that you always check the reflectance value on the substrate. And if required, you see that the reflectance value you read on the substrate, for example, for sapphire, it will be 7.5%. You read other values, you need to perform the reflectance calibration. Well, now Heiko will report typical issues what we received from the field, or what we do see in many cases in the field, what might happen.
Yes. So, as Oliver explained, there's a high importance that the boundary conditions are maintained and are all fulfilled in order to achieve a consistent, correct, true temperature. Now, this is going to list some typical root causes or errors we see, and we have seen over our time, during our time of field service support and direct customer or user support, and which we typically are still seeing today. So it doesn't mean that the entire environment is very, very error causing many errors, but it's mainly the errors caused by wrong operation or wrong handling. So to start with, the very common effect we can see is that the absolute T is either not calibrated anymore, or in some rare cases was even defect, meaning that the emission was no more calibrated, was no more consistent to its reference values to reflect the corresponding intensity for the temperature of it is calibrated to for 950 nanometers emission. So this root cause will have a direct impact to temperature calibration, the so-called delta calibration. Delta is the name of the calibration factor the EpiNet calibration sequence will determine out of this calibration. So it's essentially important that you treat your absolute T carefully, always keep it in the safe container, and more important than make sure that it's calibrated within the recommended calibration cycles as mentioned in the manual and in the paperwork of the absolute T. If you see any a significant offset or inconsistency in the resulting delta or consistency of the true temperature when you do the true temperature or EPTT calibration, even though the absolute T you are using is just recently calibrated or even within the valid calibration period, then it's highly recommended to turn it back into LayTec to have it inspected or maybe even repaired. So along with the absolute T, what we really see from time to time is that the absolute T is in perfect order and it's calibrated and it's working correctly, but still the users achieve a wrong delta value when they do true temperature calibration. And in such cases, it has happened, and it's from time to time happening that users perform a wrong handling of the absolute T. It definitely needs to get some exercise or some feeling, so to say, how to correctly handle and hold the absolute T attached to the aperture of the APTT measurement path. It's important to check the real sensitive sweet spot, so to say, for the maximum intensity or the center of the plateau of intensity in both directions, back and forth. So what typically sometimes happens is, or what you can see is that customers or users just stop at the very first spot where they think or interpret the reading as being the maximum reading, but in fact have not achieved the real center of the entire maximum intensity area. So even though you would hold the absolute T right into the center axis of the viewport aperture, it still might lead to a wrong result in delta calibration if you don't hold the face plate or the face surface of the top cover of the absolute T flush to the opening or to the ceiling or to the reactor lid. This can lead to the emission is reflected or clipped by a sidewall or an edge of the optical channel of the viewport of the aperture, and then again lead to a wrong delta calibration because the amount of light reaching the detector for that particular temperature on 950 nanometers or 405 nanometers in terms of the parallel 400 does not correspond to the expected reference value. Yeah, maybe I can go back to this picture and this slide quickly. What I'm talking about is the gray top cover on the right picture and the right-hand side bottom picture. And that's the absolute T with the gray top cover. And you can see the opening in the center of this gray plastic cover. And for correct positioning, it's important to place the entire surface flush to the mating surface of the reactor lid or of the surface that offers the aperture for the APTT reading. Okay, back to the overview. Some users still like to use eutectic wafers for calibration, and they definitely have established and qualified a reliable and repeatable procedure to do that. Although we sometimes see and get reports that apparently the evaluation of the state-changing spot of the eutectic wafer has either not been met correctly or maybe the thermal process to reach that specific temperature hasn't been maintained well enough or has been too quick, so that the users missed the spot and then calculated or derived a wrong temperature spot to calibrate for the delta calibration. Misalignment is a very essential and really important item. Misalignment refers to the general optomechanical alignment of the entire setup of the epicurve TT or the epi-TT, or even of the Pyro 400 or P400 unit. You might all know that the epi-TT as well as the epicurve TT, consisting of the epicurve laser head with the epi-TT head attached to it, are mounted on top of the reactor, on top of the viewport, with a mounting unit. And this mounting unit allows a fine positioning adjustment or alignment adjustment in both a linear Cartesian X and Y orientation, as well as an angular tilt adjustment in both directions, in a radial adjustment as well as in a tangential angular adjustment. So this alignment is the key parameter for the entire setup quality of the optomechanical components the epicurve TT or the epi-TT system consists of. And misalignment will definitely lead to impact on both the delta calibration as well as the alpha calibration, because misalignment can lead to that either the epi-T light beam or the space angular area, the light beam enters the reactor area with, can be clipped by the edge of the aperture or the viewport, or can even cause side reflections, artifacts, which have a catastrophic impact to the consistency of the optical measurement. And this will also affect the alpha substrate normalization or alpha calibration, however you call it, because if the amount of light, the reflectance measurement and the reflectance reference measurement and calibration is relying on is not consistent, it's easy to understand that the reflectance calibration typically done later on during process control will also be wrong. Window coating is something which is more or less inherent with the deposition process of the MOCVD process itself. And a slight window coating is more or less a typical gradual effect from a run to run over a run cycle sequence between scheduled maintenance periods. It's important to monitor the effect very carefully, because in worst cases, and Oliver can confirm that we have seen viewports almost completely black from almost complete deposition. In such a worst case, the dampening factor to the light transmissivity is extremely high and can, in the worst case, then affect both the delta calibration for temperature calibration as well as the alpha calibration factor for the reflectance calibration. Now, there's a very nice and very helpful feature in the new EpiNet 2 software. I think this will be addressed in the later presentation slides coming this afternoon as well. It's the so-called alpha history. So the EpiNet software, similar to how the EpiNet 1 software did, the EpiNet 2 software also maintains a bookkeeping of each record of the alpha parameters for all wavelengths. And the nice feature the EpiNet 2 software now offers is that you can easily load the full history of the alpha values in a very nice view chart within the software. It's very easy. There's a function button in the top menu bar showing alpha letter, the Greek alpha letter. And if you click on it and select your measurement system that is currently configured for this EpiNet software, select your time period you want to browse the alpha values for, then it immediately lists all alpha values with for all active channels that are configured in the EpiNet software, as well as for all wavelengths. This function comes very handy as a very helpful tool to support regular maintenance and keep a close eye on a gradual effect of window coating, even in case of damages like breaking parts or damaged or broken parts within the entire viewport assembly can easily be detected by a significant sudden jump in the resulted alpha value. So it's easy to imagine if there's a severe coating on the window or anything else is blocking the or is impacting the transmissivity of the viewport, the a subsequent alpha calibration will result in a very high alpha value. So it's leaving the typical gradual development of alpha or change curve of the alpha values, and is then showing a sudden jump. Excuse me, we have to maintain some Windows issue here. Sorry. All right, and this alpha, I really like this alpha history function very much, and it really helped me in my field service visits at some customers already to find broken fiber cables or swapped fiber connectors or other damages on the optomechanical setup. Yeah, I mentioned this, damaged fiber cables. That does not mean that the fiber cables are fragile as a raw egg or something, or like thin glass, and they are quite robust. But on the other hand, you have to maintain them pretty well and treat them pretty well in order not to damage the inner fiber core. You may keep in mind that the inner core has a diameter of 600 micrometer and only allows a minimum bending radius. Any radius smaller than the minimum allowed bending radius bears the very high risk to damage or to crack this inner fiber core. A damaged fiber cable, it's easy to understand that this will have a direct impact on the initially calibrated transmissivity of this cable for possibly both the light source cable as well as for the detector cable. And such an impact on the transmissivity will have a direct impact on both temperature calibration, the delta calibration, as well as for alpha calibration when you do reflectance calibration. Damaged fiber cables does not mean that in every case, when you find a damaged fiber or a fiber cable is damaged, that the transmission is immediately cut down to 0%. It's more like that the transmissivity is no more constant anymore and is really fluctuating and is very sensitive to vibration or motion or even changing by small hits. We've seen effects that when the process vacuum pump is kicking in at maximum pumping performance at low pressures with a high gas flow, that even slight vibrations on the system, which definitely do not affect the growth process, can affect the transmissivity and they can show a change in the amount of light that's transmitted through the fiber cables. We'll see some plots about this effect then later on. What also can happen sometimes is that the fiber's connections, typically at the fiber optical head of the APTT, can accidentally be crossed This can easily happen if you don't pay attention to it when you disconnect the fiber cables from the head, maybe for cleaning the reactor lid area or the glove box, or for repair works or leak tests work or whatever. And if you reconnect them and don't pay attention to the correct placing, it can easily happen that you cross the connections. Typically, the fiber cables are marked by some clips at the end, right at the end, where the connector is connecting to the fiber optical head. It indicates the fiber cables that feed the light from the light source, and the fiber cable that receives the light back to the controller, to the detector. In principle, you may get the impression that at the first glance that the EPTT is still working, but in fact the entire balancing and calibration and consistency of the amount of lights is completely disturbed with crossed fibers. So as a side effect, then this definitely will have an impact on delta and alpha calibration. The calibration will still, sequences will still run and reveal a delta and alpha result, but the results will definitely be wrong. And that will definitely ruin any true temperature in the system. This is a more software-related and not hardware-related root cause for a typical error. We sometimes see that users set up their wafer table in a wrong way and don't maintain a consistent wafer table setting. Well, you all might know wafer table is the typical term as it has been used in, or is still used in EpiNet 1. Now in EpiNet 2, there's a very nice graphical wafer table editor, the so-called runtime editor, and it very easily walks you through the process of configuring your measurement setup. And actually, the result of the runtime editor then ends up in a wafer table. So the final configuration result is the same equivalent wafer table setup as in EpiNet 1. So what can happen is that users declare wrong substrates, like if you don't pay attention and configure sapphire or silicon, whereas the process is running on sapphire substrates, or any other mishmash of substrates, will definitely have an impact on the correct reference calibration. Sometimes users load previously recorded or saved templates back into the runtime configuration, and if you don't pay attention, then you will easily set up a wrong wafer table. Sometimes we see that measurement zones set to the outer zone of the substrates are placed way too far out. So there is a certain risk if you users place if you place a measurement zone right to the edge of the substrate, that it can collect too much data and measurement data from the edge exclusion zone of the substrates, and even in very rare cases, we have seen that even part of the graphite is already contributing to the signal of that measurement zone. So depending on the amount of this error, of this impact, it can have even a severe impact to the complete averaging of your true temperature of that zone averaged across a full rotation. Similar can happen if you're using PSS substrates, and this can also lead to a wrong reference calibration due to the challenging structure of PSS substrates. Also, There's a very nice feature that's a new feature in EpiNet version 2 that allows you to pre-check the consistency of your measurement setup. And this is a very helpful tool. It comes very handy to make sure you do not accidentally start a measurement or configure a measurement to be started during epitaxy growth process with the wrong setup. Another case we occasionally see is that users are mixing up hardware components from different measurement systems to rebuild and recomplete an EPIC-FTT measurement system. And we've found cases, I've seen cases where computers, controllers, or modules out of a controller from a different system have been recombined to build to complete the EPIC-FTT system again. And this will, first of all, this will, in the first place, lead to wrong calibration parameters being active then for that combination of system hardware. Because you must keep in mind that the entire system, as it is shipped from LayTec, is calibrated to its dedicated hardware and components and even software components, including calibration parameters, configuration files, and additional meta information in the system. Once you mix those units or even configuration data, it will immediately destroy the consistency of the EPIC-FTT system. Furthermore, if you would do this on newer systems which are still under warranty, please be aware that this will immediately void any warranty of the affected systems. Another challenge can be transparent materials. I've mentioned this already before. It's has to be carefully maintained if you're using transparent materials as a reference substrate material for calibration. It might result in or temperature measurement. It might result in that you miss the real true temperature due to the transparency of the material. Further down then during crystal growth or layer growth, one impact or a root cause for a wrong true temperature measurement can be surface properties like rough surfaces, rough morphology of surfaces, or even of layer interfaces, for example, in terms of a rough nucleation layer interface can have an impact on the correct consistency of the true temperature calibration. Yeah, so this is only a short overview about the typical errors we more or less see in our daily work, and it's important to maintain and to be aware of these possible root causes, and then important to maintain the correct maintenance procedures to avoid those impacts. Okay, so I hand over to Oliver now to give some recommendations.
Yeah, thank you, Heiko, showing the typical things we have. We got reported from the field, from you as the customer. They had trouble with the systems, and what do we recommend to avoid such things is very easy. Is to use the raw voltage. The raw voltage is the voltage the detector is showing for the different wavelengths available in the current systems. It's 405 nanometer in the standard system, 633 and 950 nanometer. So what we would expect if the system alignment is fixed, it's correct, and the viewport is clean from run to run. You have a small fluctuation, but overall you have a straight line. You have always the same voltage since the optical path is the same. What we recommend is to insert a silicon wafer for that, to check it, to open the window. In the afternoon session during the live demo of the EpiNet 2, Thomas Mann will show how to do that in the EpiNet 2 and to track it. Here, I explained that the clean viewport is important. Maybe something to add also for the absolute maintenance. You need to keep the absolute clean as well. You will have the same effect. There's light emitted to make a hot wafer. If by moving the absolute under the ceiling or with contact to the ceiling, it might happen that over the time you accumulate a lot of dust on the window of the absolute. And that will have a similar effect, that it will influence your calibration setting. And what I have seen or got reported from my production team when they do the recalibration of the absolute, that it's sometimes very dusty, and this will happen. This will influence your measurement very strongly. I have seen several degrees C. So, and I think this will set your product very, very strongly off. Yeah. So what we see, if, for example, in the viewport is coated, what Heiko already explained is normal behavior of the tool, even when the viewport is purged properly. After a certain time, you will see in the substrate voltage a certain decrease, a continuous decrease of the intensity. This is not normal. So the first check you should do is, are all wavelengths affected with the same ratio? It might occur that the shorter wavelength is affected more strongly. This leads to the assumption that the window coating is happening. Or a light source can be also at the end of the lifetime. So it's LED based. The lifetime is several years, but after several years, there will be an end of lifetime. And we have seen not all of you are using the three wavelengths at the same time. We found also in the field that somebody also didn't recognize that also already one wavelength was missing. Yeah, it was unfortunately the one he is not using. For the end of the lifetime, you receive together with the LayTec system, and this is maybe very important to mention, not everyone is aware of that, you receive a calibration protocol. There's clearly written what voltage we have measured with the same optical path on the silicon wafer, and you can compare to your current value. And the decrease is possible for as mentioned, for individual wavelengths as well. So what also might happen is, or are sudden drops. Heiko mentioned that. It's very important to check what have you done before the drop happened. It might be possible there was a reactor maintenance, you cleaned the glove box or the ceiling, or something from the tool was removed and it was installed again. So that's indicating that something is misaligned. If this is returning, well, or you need, first of all, we need to check the distance to the optical head, the position, and what Heiko explained as well is probably the fiber cable has been broken, the glass fiber. So that might change suddenly, or it will change suddenly, but at least by opening and closing the reactor already, the fiber is moving a little bit. So sometimes you will have one intensity, sometimes another. So you will see that kind of drops, yeah, instead of seeing a continuous decrease. or the fibers might be kinked, or the bending radius is too small, or is changing because the fiber isn't installed properly. Well, what we recommend, if the intensity, just going back to the other slide, is decreased by 50%, you should exchange the light source. Here you see what the current software, the EpiNet 2, the configuration panel. So you select the wavelengths, you can compare the voltages as shown for all the wavelengths. So, and for example, a stronger decrease in the 405 nanometers in the nitride process indicates that the window coating is started. The 405 nanometer is absorbed as first. So, and you have the possibility to save the line scans, to make a screenshot for your documentation. Well, to define everything in the wafer table, Thomas will show that as well in the afternoon session. So this is a new procedure. Well, what to do if the intensity drops? So suboptimum alignment means you need to realign it. Please refer to the manual or contact LayTec, contact Aixtron, the tech support, or the LayTec service partner if you are in a region where we have our service partners. Well, if the window is coated, I heard for different technologies when I have done that, it was always a wet cleaning. So you have etched the viewport window in some kind of acid mixture. But I saw now also some dry cleaning methods. Both is possible. The only important thing is, Heiko was just agreeing that also dry cleaning is possible.
Yeah, it depends on the amount of coating. Sometimes even cleaning it with a Q-tip with IPA might be sufficient. Depends.
And as mentioned, if the light source degradation, that's really significant. That means, and this is also mentioned in your calibration protocol, is less than 50% of the initial intensity. We strongly recommend to start to exchange a light source, contact LayTec or contact Aixtron. If you are still able to work, but this is the right time to start to get the replacement part. And here, because we have mentioned for the problems we received from the field is, you will receive new calibration data related to the new light source. This is important. And also if some of you are also using replacement PCs, they have just in case that in the stock can have a sudden reaction, a quick reaction to get the system running again. We will support you to get the calibration data on the new computer. And then, hardware mixing sounds very bad. We will enable you to do that. What we like to mention is just you need to be careful. You cannot just do that. So, and as long the decrease of the light source degradation is not so significant, it's a slight decrease, this is normal lifetime, so over the time the intensity will decrease. You need to perform the reflectance calibration. This will compensate this effect. So, what means correct reflectance calibration? In that case, we show that for the sapphire wafer. So that means on the substrate, we do expect a reflectance of 7.5%. So if we do the reflectance calibration properly, we will have a straight temperature line without any oscillations. If we would do that with the wrong value, in that example, this is set to 5%, even this minor change of the reflection will already cause some residual oscillations. So it gets very difficult to determine the real temperature value. So, what also will help in the software is to make a scan over the full revolution of the susceptor. You should use the EpiNet display configuration panel, and you click on the workflow item susceptor phase. EpiNet software will scan all the wafers. And what we would expect if all wafers are the same, we would expect the rectangular shape reflectance envelope. In that example, we inserted to demonstrate that a different substrate, one is a sapphire wafer. Sapphire has a much lower reflection than silicon. So you see the difference immediately, that something is wrong on the third pocket. So the more the higher probability is something is not correctly aligned instead of inserting a wrong substrate, you will see that in the shape, in lower shape, and tilted shape, and oscillating shape. This is indicating that something is wrong with the alignment. So Heiko explained it already a little bit. You have the XY stages. The left-hand side are the examples for the epi curve, and you have the tilt as well. And the right-hand side is for the epi-TT. So there's always an XY phi stage that we can have the alignment of the position and the tilt. The manual is explaining how to do that. But if you feel not safe, please feel free to contact us, and we will support you to do the alignment, or we will do an on-site visit, or Aixtron will do the on-site visit. Yeah, everything is possible. If just one wafer is affected, this also occurs. It might happen that one of the pockets is not completely flat. Can be a flake coming from the ceiling, or sometimes there's also a certain lifetime of the pockets. So it might be not completely flat. So you need to remove the flake, or you need to remove the pocket, the satellite, or however this is done in your tool. And you need to double check that the wafer is really flat and you have this rectangular shape of the reflectance pattern. So, and that means finally the epi-TT and epi-curve TT is not only for the growth analysis, it also enables you to check the quality of the growth start already. Yeah, are you able to have the expected quality of the growth later on? So I can just repeat it. Please attend the afternoon live demo for the EpiNet 2. So Thomas 1 will show the new features and how to do that in the EpiNet software. So this brings us finally to the conclusions.
Yes, thank you, Oliver. Yeah, I would like to summarize the conclusions quickly. So I hope we could make clear that the in-situ metrology and the proper consistency of the in-situ metrology system and its integration into the MOCVD production is very important to give the key property for optimization of productivity and the cost of ownership. The key parameter in the entire system is definitely the true temperature, which is depending on a broad variety of boundary conditions, as we just have explained. So the bottom line is always ensure a valid calibration, ensure a correct setting in the entire system, also on the MPC itself, including low-level configuration setting as well as run type or wafer table setup. Be careful with any changes on the system in order not to destroy the entire system calibration or consistency. Always check the in-situ metrology status on a regular basis. Put it to your regular scheduled maintenance period along with the MOCVD system. It's important to maintain both the metrology system as well as the entire MOCVD system in terms of cleaning viewports and wafer positioning and so on, in order to maintain the consistency of the entire system. Yes. Okay. Next slide.
Yeah.
Sorry.
Well, and an outlook for the Aixtron and LayTec for our common customers. Since a long time, we are planning a joint knowledge tour, yeah, to discuss with you much more detailed challenges in your growth system, how to use the LayTec tool. The current schedule is still influenced by COVID-19 travel restrictions. So Heiko and me, we are on a regular basis discussing the changes in the schedule. Currently, I think we do expect something in Q4, where we are now. So, but we need to see how we can do that. If we will still have strong restrictions, we are already planning also online sessions. Yeah. So please feel free to contact us via the channels mentioned in the beginning. So finally, yes, I think you know we are still working on continuous improvement of both sides, improving the MOCVD systems, improving the LayTec systems, and especially we are working very close together to improve also the interaction between two worlds, in-situ metrology and MOCVD. To meet your future production requirements. Sure. Yeah, thank you.
Yeah.
For your attention.
Yeah, thank you very much for your attention, and I hope we could make some very important points more clear to you and could be helpful in increasing understanding and giving clarity. And we will be happy to answer any question or comments through the channels given.
Okay, Oliver, Heiko, thank you very much for the great talk. Unfortunately, we are running a bit behind time, so I would say that we postpone the questions to the live demo, which will also give us the possibility to see the system working live, and this may raise another question or two. So thank you very much again, and I will then take over to the next talk.
Yep. Thank you.
Thank you. Bye-bye.
Bye.